In the depths of the Mediterranean Sea, near the rocky shores of the Greek island of Antikythera, a team of sponge divers was searching for marine sponges in the spring of 1901 when they stumbled upon something strange. Among the wreckage of a sunken Roman ship, they noticed broken statues and clay pottery. But among those artifacts lay a corroded metal object covered in thick layers of calcified deposits. At that moment, they had no idea they were looking at a discovery that would completely overturn our understanding of ancient history. The artifact was transported to the National Archaeological Museum in Athens, where it remained for decades, a perplexing enigma among other treasures. At first, scholars thought it might simply be a piece of a medieval astronomical clock, perhaps accidentally lost in the wreck. But as time passed, the truth slowly began to emerge. This mysterious device, later named the Antikythera Mechanism, turned out to be the oldest known mechanical astronomical calculator in the world, crafted by the Greeks over 2,000 years ago. British physicist Derek de Solla Price was among the first to recognize the significance of this discovery. In the 1950s, he began carefully studying the artifact using the imaging techniques available at the time. He noticed that the preserved metal was not just an ordinary plate, but contained intricate interlocking gears. The astonishing revelation was that such technology was not thought to exist in the ancient world. Historians had long believed that machines of this complexity did not appear until the European Renaissance. Yet the greatest challenge lay in the mechanism's corroded state. After centuries underwater, it had turned into a solid mass of rust and lime, making its secrets nearly impossible to decipher. In the 1970s, Price and his colleagues used X-ray technology to penetrate the outer layers, revealing a complex system of internal gears. Still, much of the mechanism's function remained a mystery due to the limitations of the technology at the time. At the turn of the 21st century, a breakthrough occurred when an international team led by astronomer Michael Edmonds and mechanical engineer Michael Wright applied advanced 3D imaging and high-resolution X-ray technology. The scans unveiled astonishing details. Dozens of tiny gears, some with teeth as small as a millimeter, engineered with precise mathematical calculations. Inscriptions in fine Greek lettering also appeared on the inner surfaces, serving as a kind of user manual for the device. By analyzing the inscriptions, researchers discovered that the mechanism was used to predict the movements of the Sun, Moon, and even planets like Mercury and Venus. It could calculate the timing of solar and lunar eclipses with remarkable accuracy and even included a calendar for the ancient Olympic Games. Most astonishingly, some of the gears simulated the irregular orbit of the Moon, an astronomical calculation so advanced that it was not thought to have been understood until centuries later. But the biggest question remained: who built this ingenious device? Evidence suggests it was designed in the 1st century BCE, likely on the island of Rhodes, a hub of science and astronomy at the time. Some historians believe the philosopher and scientist Posidonius may have been involved in its creation, while others speculate it was the work of unknown engineers following the teachings of Hipparchus, one of the greatest astronomers of antiquity. Today, more than a century after its discovery, the Antikythera Mechanism continues to astonish scientists. It has transformed our understanding of ancient Greek technology, proving that civilizations of the past were capable of creating complex machines 2,000 years before the age of computers. With every technological advancement, new studies uncover more of its secrets, reminding us that history may hold endless surprises yet to be revealed. On a cloudy spring afternoon in 1901, a team of Greek sponge divers exploring the murky waters near the remote island of Antikythera had no idea. They were about to uncover one of humanity's greatest historical mysteries. Their eyes searched for valuable sponges among the seabed rocks, but what their hands discovered was something entirely different, an artifact that would shake our understanding of ancient civilizations. From the wreckage of a Roman ship dating back to the 1st century BCE, strange pieces of corroded bronze began emerging from the sand and seaweed, not like the usual statues or pottery they typically found, but rather a mysterious metal mass covered in thick layers of calcified deposits. The divers brought their discovery to archaeological authorities in Athens, beginning a long journey of examination and study. Initially, scholars thought this was merely part of a medieval astronomical clock that had accidentally fallen into the wreckage. But as years passed, the truth gradually surfaced, a truth more astonishing than any fiction. They were looking at an intricate mechanical astronomical calculator over 2,000 years old, crafted with unbelievable sophistication by ancient Greek artisans. British scientist Derek de Solla Price was among the first to recognize the significance of this astounding discovery. In the 1950s, he began studying the mysterious artifact using the imaging technology available at that time. His findings were breathtaking. Inside that corroded metal mass were precisely interlocking gears, arranged in a complex geometric system. This revelation shocked the scientific community, as no one had imagined such advanced technology existed in ancient times. Historians had always believed machines of this complexity only appeared during the European Renaissance, more than 1,000 years after this mechanism's creation. The real challenge lay in the mechanism's deteriorated condition. After centuries, on the seafloor, it had transformed into a solid mass of rust and lime, making the task of decoding its secrets nearly impossible. In the 1970s, Price and his colleagues used X-ray technology to penetrate the outer layers, revealing an intricate system of internal gears. Yet much of the mechanism's function remained mysterious due to technological limitations of the era. At the dawn of the 21st century, a qualitative leap occurred when an international team led by astronomer Michael Edmonds and mechanical engineer Michael Wright employed advanced 3D imaging and high-resolution X-ray technology. The new images revealed astonishing details: dozens of tiny gears, some with teeth no larger than a millimeter, engineered with precise mathematical calculations. Minute Greek inscriptions also appeared on internal surfaces, serving as a kind of user manual for the device. Through analyzing the inscriptions and gears, researchers discovered the mechanism could predict the movements of the Sun and Moon with astonishing accuracy, even tracking planets like Mercury and Venus. The device used the famous Saros astronomical cycle, an 18-year period predicting eclipse recurrence, to calculate the timing of these celestial phenomena decades in advance. Most remarkably, some gears simulated the moon's irregular motion, an astronomical calculation so precise it wasn't thought to have been understood until centuries after this mechanism's creation. But the biggest question perplexing scientists remained: who built this ingenious device? Evidence suggests it was designed in the 1st century BCE, likely originating from a workshop on the island of Rhodes, then a center of science and astronomy. Some historians believe the Greek philosopher and scientist Posidonius might have been involved in its design, while others speculate it was the work of unknown engineers following the school of Hipparchus, one of antiquity's greatest astronomers. Today, over a century after its discovery, the Antikythera mechanism continues to astonish scientists while raising more questions than answers. This small machine has transformed our understanding of ancient Greek technology, proving that ancient civilizations were capable of creating complex machinery 2 millennia before the computer age. With every new technological advancement, modern studies reveal more of its secrets, reminding us that history's pages may hide endless surprises, and that the greatness of the human mind knows no temporal bounds. In a bygone era, when the Roman Empire stood at the pinnacle of its power, and the Mediterranean Sea was essentially a Roman lake, a massive merchant ship sailed laden with priceless treasures. This vessel, which sank near the small island of Antikythera, carried within its hull a technological secret that would remain buried beneath the waves for over 2,000 years. No one could have imagined that among those looted artifacts and shattered vases would be discovered the most complex mechanical device the ancient world had ever known. On that fateful day in 1901, as Greek sponge divers plunged into the azure depths, their dreams extended no further than finding the precious sponges that provided their livelihood. But destiny had prepared for them a surprise from antiquity. Suddenly emerging from the seaweed and scattered stones were strange bronze shapes unlike any statues they had seen before. These corroded fragments concealed a mystery that would perplex scientists for more than a century. When news reached the National Archaeological Museum in Athens, researchers initially treated these strange metal pieces as mere secondary artifacts, among the more glittering treasures recovered from the wreck. No one realized at the time that they were looking at what could be considered history's first analog computer, a discovery that would completely overturn prevailing notions about ancient technology. As years passed, the mysterious bronze artifact attracted the attention of some curious researchers while being forgotten by others. In the 1950s, British physicist Derek de Solla Price began a meticulous study of this archaeological enigma. Using the imaging technology available at the time, extraordinary features began emerging from within that corroded metal mass. There were gears, precise interlocking gears in a complex system. This discovery alone was enough to revolutionize understanding of ancient technology. But the real story began unfolding at the dawn of the 21st century, when an international team of scientists employed advanced 3D imaging and high-resolution X-ray technology. What these examinations revealed was astonishing by any measure. Dozens of small bronze gears, some no more than a few millimeters in diameter, engineered with breathtaking geometric precision. Delicate Greek inscriptions covered inner surfaces, like an instruction manual accompanying the device. They were looking at an advanced astronomical calculator centuries ahead of its time. What most amazed researchers was discovering that this mechanism could track planetary movements, predict solar and lunar eclipses, and even calculate dates of the ancient Olympic Games. All this was made possible by an intricate system of rotating gears that simulated celestial movements according to mathematical laws established by Greek astronomers. But how had this advanced mechanical knowledge reached the ancient Greeks? Who were the geniuses behind this miraculous device? Evidence suggests the answer may lie on the island of Rhodes, that flourishing scientific center of the Hellenistic period. Perhaps the philosopher Posidonius, or possibly students of the great astronomer Hipparchus, stood behind this astounding technological achievement. Today, more than a century after its discovery, the Antikythera mechanism continues to raise more questions than it answers. With every new technological advancement, scientists uncover another layer of complexity in this marvelous device. This unique artifact has transformed our understanding of humanity's technological history, proving that human genius knows no temporal boundaries. It reminds us that ancient civilizations may have been far more advanced than we imagine, and that the blue depths of the Mediterranean still guard many secrets within their waters. It was a scientific earthquake that shook the world when the secrets of the Antikythera mechanism began to gradually unfold. This marvelous device, buried in the depths of the Mediterranean Sea for over 2,000 years, was no ordinary artifact. It stood as tangible physical evidence of ancient human genius that historians had long underestimated. At that historic moment when scientists realized they were looking at an advanced astronomical calculator dating back to the 1st century BC, many concepts about humanity's technological progress were forever changed. The scientific community had always believed such complex technologies only emerged during the European Renaissance, when Swiss watchmakers began crafting precision gears and Leonardo da Vinci created his remarkable mechanical drawings. But the Antikythera mechanism declared to the world in unequivocal terms, "The ancient Greeks beat you to this 2,000 years ago." This mechanism served as a scientific slap in the face to anyone who had underestimated ancient capabilities. When scientists began examining the precise gears comprising the mechanism, they discovered these weren't just random bronze pieces, but rather a complex system that remarkably mimicked celestial movements. The ancient Greeks, without any modern technology, had calculated the moon's irregular motion, predicted solar and lunar eclipses, and even tracked the paths of known planets, all through an exquisite mathematical geometric system relying on precision gears, some measuring just millimeters in diameter. What's most thrilling about this story is how the mechanism transformed our understanding of humanity's technological history. It proved that technological progress isn't linear as we once believed, and that ancient civilizations may have achieved levels of development we wouldn't have credited without physical evidence like the Antikythera mechanism. This discovery forced historians to reconsider many ancient texts previously dismissed as fanciful or exaggerated. The mechanism's greatest impact has been on modern mechanical engineering. When contemporary engineers studied its gear design, they were astonished by its geometric precision. The ancient Greeks used what we now call differential gearing, the same principle employed in modern automobile transmissions. This revelation inspired many modern engineers to reevaluate concepts they believed were entirely contemporary. In astronomy, the mechanism provided physical proof that ancient Greeks employed highly advanced astronomical calculations. They managed to combine both the Saros and Metonic astronomical cycles into a single mechanical device. These eclipse prediction cycles weren't thought to be calculable with such precision in that distant era. This discovery compelled astronomers to reassess much ancient astronomical knowledge. Technologically, the Antikythera mechanism inspired new imaging techniques. Because the mechanism was severely degraded from centuries underwater, scientists had to develop advanced 3D imaging technologies to study it without causing damage. These techniques, originally created for the mechanism, are now used in various medical fields for high-precision internal imaging. In analog computing, the Antikythera mechanism stands as the grandfather of all mechanical computers. It proved that using mechanical gears for complex calculations isn't as modern as we thought. This discovery gave significant momentum to mechanical computing research, opening possibilities for developing precision mechanical computers that could operate in extreme conditions where electronic computers fail. Culturally and educationally, the mechanism changed how we view ancient civilizations' achievements. It has become a symbol of human creativity and the mind's capacity for innovation across all ages. Today, scaled models of the mechanism teach students mechanical engineering principles and astronomy, making history come alive before their eyes. But perhaps the most important lesson from the Antikythera mechanism is that technological advancement isn't exclusive to our modern era. This unique artifact proved that human genius knows no temporal bounds, and that ancient civilizations may have been far more advanced than we imagine. This discovery makes us wonder, what other great inventions and discoveries might be lost to history? What other technological secrets might lie in ocean depths or beneath desert sands, waiting to be uncovered and tell another chapter of humanity's astonishing creative story? It was a scientific earthquake that shook the world when the secrets of the Antikythera mechanism began to gradually unfold. This marvelous device, buried in the depths of the Mediterranean Sea for over 2,000 years, was no ordinary artifact. It stood as tangible, physical evidence of ancient human genius that historians had long underestimated. At that historic moment when scientists realized they were looking at an advanced astronomical calculator dating back to the 1st century BC, many concepts about humanity's technological progress were forever changed. The scientific community had always believed such complex technologies only emerged during the European Renaissance, when Swiss watchmakers began crafting precision gears and Leonardo da Vinci created his remarkable mechanical drawings. But the Antikythera mechanism declared to the world in unequivocal terms, "The ancient Greeks beat you to this 2,000 years ago." This mechanism served as a scientific slap in the face to anyone who had underestimated ancient capabilities. When scientists began examining the precise gears comprising the mechanism, they discovered these weren't just random bronze pieces, but rather a complex system that remarkably mimicked celestial movements. The ancient Greeks, without any modern technology, had calculated the moon's irregular motion, predicted solar and lunar eclipses, and even tracked the paths of known planets, all through an exquisite mathematical geometric system relying on precision gears, some measuring just millimeters in diameter. What's most thrilling about this story is how the mechanism transformed our understanding of humanity's technological history. It proved that technological progress isn't linear as we once believed, and that ancient civilizations may have achieved levels of development we wouldn't have credited without physical evidence like the Antikythera mechanism. This discovery forced historians to reconsider many ancient texts previously dismissed as fanciful or exaggerated. The mechanism's greatest impact has been on modern mechanical engineering. When contemporary engineers studied its gear design, they were astonished by its geometric precision. The ancient Greeks used what we now call differential gearing, the same principle employed in modern automobile transmissions. This revelation inspired many modern engineers to reevaluate concepts they believed were entirely contemporary. In astronomy, the mechanism provided physical proof that ancient Greeks employed highly advanced astronomical calculations. They managed to combine both the Saros and Metonic astronomical cycles into a single mechanical device. These eclipse prediction cycles weren't thought to be calculable with such precision in that distant era. This discovery compelled astronomers to reassess much ancient astronomical knowledge. Technologically, the Antikythera mechanism inspired new imaging techniques. Because the mechanism was severely degraded from centuries underwater, scientists had to develop advanced 3D imaging technologies to study it without causing damage. These techniques, originally created for the mechanism, are now used in various medical fields for high-precision internal imaging. In analog computing, the Antikythera mechanism stands as the grandfather of all mechanical computers. It proved that Using mechanical gears for complex calculations isn't as modern as we thought. This discovery gave significant momentum to mechanical computing research, opening possibilities for developing precision mechanical computers that could operate in extreme conditions where electronic computers fail. Culturally and educationally, the mechanism changed how we view ancient civilizations' achievements. It has become a symbol of human creativity and the mind's capacity for innovation across all ages. Today, scaled models of the mechanism teach students mechanical engineering principles and astronomy, making history come alive before their eyes. But perhaps the most important lesson from the Antikythera mechanism is that technological advancement isn't exclusive to our modern era. This unique artifact proved that human genius knows no temporal bounds, and that ancient civilizations may have been far more advanced than we imagine. This discovery makes us wonder, what other great inventions and discoveries might be lost to history? What other technological secrets might lie in ocean depths or beneath desert sands, waiting to be uncovered and tell another chapter of humanity's astonishing creative story? What challenges did scientists face when trying to decipher the Antikythera mechanism? Deciphering the Antikythera mechanism presented scientists with a series of extraordinary challenges that spanned over a century of research. When the corroded bronze fragments first emerged from the Mediterranean depths in 1901, researchers confronted what appeared to be an indecipherable metallic clump, its original form completely obscured by 2 millennia of marine incrustation. The initial obstacle was simply determining what they were looking at. The calcified lump bore little resemblance to any known ancient artifact, and its intricate internal structure remained hidden beneath layers of hardened sediment and corrosion, products that had fused the components into a single mass. As early investigators like archaeologist Valerio Staes and physicist Derek de Solla Price began their examination, they faced the fundamental dilemma of how to study the mechanism without destroying it. The technology of the early 20th century offered limited tools for non-invasive investigation, forcing researchers to rely on visual inspection and rudimentary X-ray imaging that provided frustratingly incomplete glimpses of the internal structure. Even when these early X-rays revealed the presence of gears in the 1950s, the images lacked sufficient resolution to determine how these components interacted or what their precise functions might be. The mechanism's state of preservation presented a nightmare scenario for conservators. The bronze had mineralized into a fragile, layered structure where corroded metal alternated with marine deposits, making any attempt at physical separation potentially catastrophic. The 1970s brought new challenges as researchers realized the mechanism's complexity far exceeded initial estimates. Gamma-ray imaging by Charalambos Karakalos revealed more gear teeth, but also exposed the limitations of contemporary imaging technology. Crucial details remained obscured, and the three-dimensional relationships between components were impossible to reconstruct from two-dimensional images. Scientists struggled with the paradox of an artifact too delicate to disassemble yet too complex to understand without seeing its internal workings. This period saw frustrating dead ends as various theories about the mechanism's function were proposed but couldn't be conclusively verified. The turn of the 21st century introduced both new opportunities and new complications. Advanced 3D X-ray tomography finally allowed researchers to virtually unwrap the mechanism's layers, but this process generated enormous datasets that required innovative computational approaches to interpret. The high-resolution scans revealed inscriptions and gear trains previously invisible, but these discoveries brought their own puzzles. The tiny, corroded Greek letters, often less than 2 millimeters tall, were fragmentary and required painstaking reconstruction, while the gear arrangements implemented mathematical relationships that didn't match any known ancient astronomical theories exactly. Perhaps the most profound challenge was conceptual. Scientists had to overcome their own assumptions about ancient technological capabilities. The mechanism's sophisticated differential gearing and precise astronomical calculations contradicted the prevailing historical narrative about ancient Greek technology. Researchers found themselves simultaneously trying to reconstruct a damaged physical object and reimagine an entire intellectual tradition that could have produced such a device. This required unprecedented collaboration between archaeologists, physicists, astronomers, philologists, and historians, each bringing different methodologies and facing communication barriers across their specialized fields. The final ongoing challenge remains the mechanism's incompleteness. With only about 82 fragments recovered, representing perhaps 1/3 of the original device. Scientists must extrapolate the whole from partial evidence, knowing that crucial components may forever remain on the seafloor near Antikythera. Even today, as new imaging technologies emerge, each advance reveals previously unseen details while simultaneously introducing new questions about how this astonishing device truly functioned in its complete form. In an era when the calendar was more than just numbers on a page, but rather a living record of cosmic harmony with human rituals, the ancient Greeks invented a miraculous system connecting celestial movements to their sacred games. The Antikythera Mechanism was never just a cold astronomical instrument. It stood as testament to how the brilliant Greek mind transformed timekeeping into a vibrant mosaic where heavenly bodies and earthly events danced in astonishing synchrony. At un point, the heart of this ingenious device, nestled among bronze gears mimicking planetary motions, lay another hidden secret. Its unknown creator had designed a small dial that rotated slowly, not to track eclipses, but to preserve Greece's athletic heritage. This tiny disk, no larger than an ancient coin, contained the pulse of Greek cultural life, the sacred Olympic cycle. After centuries of meticulous study, researchers discovered this machine didn't just predict Olympic dates, but preserved timelines for 4 major athletic competitions of the Greek world: the Olympic Games at Sacred Olympia, the Pythian Games at Delphi, where divine prophecy breathed, the Nemean Games haunted by the mythical Nemean lion's roar, and the Isthmian Games where land met sea. The true genius lay in its operation. While the astronomical components calculated complex lunar cycles and solar movements through zodiac constellations, its mathematical system worked as a precision timekeeper, counting the 4-year intervals between Olympiads. The Greek maker had employed the same gears that tracked stars to also schedule humanity's most important events. Advanced 3D imaging finally revealed astonishing inscription details, not just competition names but host cities, seasonal timing, and possibly even historical victors' names. Thus, the Antikythera Mechanism wasn't merely history's first known astronomical computer, but perhaps its first sports database. Most remarkably, this feature unveils profound Greek temporal philosophy. Time wasn't linear events, but an interconnected fabric of celestial phenomena and earthly rituals. The Olympics weren't mere competitions, but part of the cosmic order governed by Olympian gods. In this light, the mechanism became a bridge between heaven and earth, science and religion, mind and spirit. This wondrous device reminded its Greek user that human life wasn't separate from cosmic movements. When athletes competed at Olympia, they weren't just exercising, but participating in a precisely calculated cosmic ritual like eclipses or full moons. This deep cosmic human connection elevated the Antikythera Mechanism beyond mechanical innovation into intellectual masterpiece. Today, as we watch modern Olympics through computer screens, we rarely recall our Greek ancestors tracked their schedules via star-calculating mechanisms. We've lost that sense of cosmic connection, but the Antikythera Mechanism remains a silent witness to an era when athletes, astronomers, and metaphysicians sat at the same table, drinking from the same cup, pondering eternal questions about time and destiny. Archimedes' mechanical orreries, as described in ancient texts, represented a breathtaking fusion of astronomical knowledge and mechanical ingenuity that far surpassed simple models of the cosmos. These intricate devices, now lost to history but referenced by Cicero and other classical writers, appear to have been sophisticated planetaria capable of replicating celestial motions with remarkable accuracy. The primary functions of these extraordinary machines went far beyond mere demonstration, serving as both educational tools and computational devices that brought the heavens down to earth. The most fundamental function was accurately modeling the movements of celestial bodies in 3-dimensional space. Unlike static representations of the cosmos, Archimedes' orreries incorporated gear trains that reproduced the relative motions of the sun, moon, and known planets with what Cicero described as divine perfection. Each celestial body moved according to its proper period, the moon completing its orbit in approximately 27.3 days, while Saturn took nearly 29 years, all simultaneously displayed through an ingenious arrangement of interlocking bronze gears. This required solving complex mechanical problems to account for different rotational speeds within a single unified mechanism. A particularly sophisticated function involved demonstrating lunar motion, including the moon's phases and its irregular orbit. Archimedes appears to have incorporated a mechanism similar to the pin and slot device later found in the Antikythera Mechanism, which accounted for the moon's varying speed due to its elliptical orbit. This produced an accurate representation of what astronomers called the first anomaly of lunar motion, something most ancient Greeks believed could only be demonstrated mathematically, not mechanically. The orreries also served as celestial calculators, predicting astronomical events like eclipses by showing the alignment of sun, moon, and earth over time. While not as specialized as the Antikythera Mechanism's eclipse prediction dial, Archimedes' devices could indicate when conditions were favorable for eclipses based on the relative positions of the celestial bodies. This function likely relied on the Saros cycle, a period after which eclipses repeat, which Greek astronomers knew from Babylonian sources. Another remarkable function was illustrating the retrograde motion of planets, the apparent backward movement that occurs when Earth overtakes other planets in their orbits. Archimedes solved this problem through epicyclic gearing, gears mounted on other gears, creating the looping paths characteristic of planetary motion against the fixed stars. This mechanical representation helped visualize a phenomenon that challenged geocentric models of the universe. The orreries also functioned as cosmic calendars, tracking the solar year, lunar months, and possibly even the 4-year cycle of the Olympic Games. By turning a hand crank, observers could advance the mechanism to see celestial configurations for any given date, or watch how the heavens would change over time. Some accounts suggest they may have included pointers or dials showing the dates of important religious festivals or seasonal changes. Beyond their practical functions, these devices served profound philosophical purposes. They physically demonstrated Archimedes' conviction that the universe operated according to mathematical laws that could be mechanically reproduced. In showing celestial phenomena as the product of regular, interlocking motions, rather than capricious divine intervention, the orreries embodied the Greek transition from mythological to mathematical cosmology. Recent research suggests Archimedes may have used his orreries to test astronomical theories, making them not just demonstrative but experimental devices. By adjusting gear ratios and observing the resulting motions, he could evaluate different explanations for celestial phenomena. This would make them ancestors of both modern planetariums and computational modeling systems. The loss of Archimedes' original orreries remains one of history's great scientific tragedies. What survives in descriptions hints at devices that were centuries ahead of their time, combining the theoretical brilliance of Greece's greatest mathematician with mechanical sophistication that wouldn't be matched until the Renaissance. They stand as testament to a level of ancient technological achievement that we are only beginning to fully appreciate. The great Roman orator Cicero stood in awe before the marvelous invention created by the Stoic philosopher Posidonius in Rhodes. His eyes widened in amazement as he beheld that extraordinary bronze sphere no larger than a big orange, yet containing within its structure the secrets of the entire cosmos. Posidonius's skilled hands had transformed raw metal into a moving model of the heavens, mimicking with its precise movements what the Greeks believed only gods could accomplish. The sphere rotated with astonishing smoothness, as if a piece of the sky had descended to earth. The small golden sun moved along its predetermined path, while the silver moon followed in its complex dance. The 5 known planets at that time, Mercury, Venus, Mars, Jupiter, and Saturn, each moved in their own orbits at different speeds, sometimes advancing and sometimes retrograding in their motion, just as they did in the real sky. This was not merely a decorative model, but a miniature universe operating according to precise mathematical laws. What amazed Cicero most was how this small device could simulate the most complex astronomical phenomena. The moon in Posidonius's model didn't move at constant speed but would slow down and then accelerate in its rotation, exactly like the real moon in the night sky. This was because Posidonius understood that the lunar orbit wasn't perfectly circular, but elliptical, making the moon appear sometimes closer and faster, and other times farther and slower. But that wasn't all. The planets in Posidonius's model performed strange, complex movements, sometimes advancing across the sky, then moving backward before advancing again. This motion, which we now know results from differences in planetary speeds in their orbits, around the sun was utterly perplexing to the ancient Greeks. Yet Posidonius managed to replicate it mechanically through an intricate system of gears and rotating circles inside his bronze sphere. Most remarkably, this model could predict solar and lunar eclipses with astounding accuracy. Posidonius had incorporated into his machine the ancient Babylonian knowledge of the Saros and Metonic cycles, those astronomical periods that predict eclipse recurrence every approximately 18 years and 11 days. The device showed how when the moon passed directly between the sun and Earth, it would block sunlight, causing a solar eclipse. Similarly, when Earth came between the sun and moon, the moon would enter Earth's shadow, resulting in a lunar eclipse. Cicero, who had studied astronomy under Posidonius himself, couldn't contain his admiration for this invention. In his work On the Nature of the Gods, he accurately described how his friend Gaius Sulpicius Gallus would rotate the sphere to explain eclipses to guests. Gallus would pause the motion at specific points, showing how the moon's shadow would fall on Earth on that exact day, or how the moon would enter Earth's shadow several months later. But the true lesson of this device, as Posidonius intended, wasn't purely technical, it was profoundly philosophical. The moving sphere served as physical proof that the universe wasn't random chaos, but a precise system governed by mathematical laws the human mind could understand and replicate. If a set of bronze gears could organize with such precision, wouldn't the universe itself, in all its complexity and beauty, testify to the existence of a supreme divine intelligence that designed it? This philosophical dimension made Cicero's description of the device particularly significant. He didn't merely describe its mechanical movements, but contemplated its deeper implications. The sphere wasn't just a scientific toy, but a bridge between the physical and metaphysical worlds, between what could be seen with the eyes and what could only be grasped by the mind. Today, more than 2,000 years after the disappearance of Posidonius's sphere, we don't know exactly what its precise details look like. But Cicero's accurate description, along with discoveries like the Antikythera Mechanism, gives us glimpses of how advanced Greek astronomical technology was. Posidonius and his fellow Greek philosophers and scientists were pioneers in attempting to understand the universe, not just through observation and contemplation, but also through mechanical imitation and simulation. Ultimately, Posidonius's sphere, as described by Cicero, remains a testament to an era when science, philosophy, art, and engineering converged in astonishing harmony. An era when scholars weren't merely passive observers of natural phenomena, but active researchers trying to understand the secrets of the cosmos, not just through abstract thought, but by transforming those ideas into tangible physical models. This perhaps is the greatest legacy left to us by Posidonius, Cicero, and other great minds of that time. In an age when measuring time was a fundamental challenge facing the human mind, water clocks stood tall as the greatest technological invention of ancient times. They were not merely tools for telling time, but a scientific revolution that changed the course of civilizations. In the temples of pharaonic Egypt, where priests sought to understand the secrets of the long night, the first primitive water clocks were born. Simple in construction, just a stone vessel leaking water drop by drop through a small opening, they represented the seed that would grow into the great tree of technology. In glorious Athens, where democracy and philosophy flourished, the water clock became an impartial judge in courtrooms. Each orator was given a fixed time measured by this marvelous device. When the water ran out, their defense time ended. Thus, this machine transformed from a mere timekeeper into a symbol of justice and equality. Some historians argue that the great art of Greek rhetoric would never have reached such perfection without this strict temporal regulator. But the Greek mind was not content with such simple applications. In Alexandria, where the great library housed the finest minds of the era, engineers like Ctesibius transformed the water clock from a primitive tool into a complex machine that astonished observers. They added gears, wheels, and floats until it could measure time with unprecedented precision. These advanced devices functioned as primitive computers, tracking not just hours of day and night, but also calculating planetary and stellar movements. In ancient China, water clocks reached a level of complexity that made them artistic masterpieces as much as scientific ones. The great inventor Zhang Heng integrated the water clock with astronomical instruments to track stars, creating a marvelous machine that displayed seasonal changes and celestial movements. This was no mere practical tool, but a material philosophical representation of astronomy, making the vast cosmos manifest in a human-made device. In the Islamic world during the golden age of Arabic civilization, water clocks reached their peak of complexity and beauty. Engineers like Al-Jazari designed massive water clocks with moving figurines that produced sounds on the hour, some even playing music. These were not just functional objects, but expressed an entire philosophy merging art with science, beauty, with utility. In mighty Rome, ruling the known world, water clocks spread everywhere, from temples to public squares, military barracks to famous Roman baths. The Romans relied on them to organize everything from Senate sessions to market opening hours. Some historians believe famous Roman precision in organization and construction would never have reached such levels without these clocks. The most fascinating story is how water clocks became bridges between civilizations. While each culture developed its water clocks independently, trade routes and knowledge exchange spread ideas from Egypt to Greece, China to the Islamic world, and onward to Europe. The water clock became a universal language transcending cultural and linguistic barriers. Most importantly, water clocks were the cradle of complex machinery. From them, humans learned how to transform continuous regular motion, water flow, into controllable, measurable movement. This fundamental principle made possible medieval mechanical clocks and underlies most modern machinery today. Ultimately, water clocks were more than timekeeping devices. They reflected ancient humanity's vision of the universe. Through them, people understood that time was not abstract but something measurable and controllable. This revolutionary idea became the foundation for all subsequent technology, from precise atomic clocks to our modern ultra-fast computers. The Antikythera Mechanism and astrolabes represented two revolutionary approaches to ancient astronomical calculation, each with distinct capabilities reflecting different philosophical and technological traditions. While both devices modeled celestial movements, their designs and functions diverged dramatically in ways that reveal much about ancient scientific priorities. The Antikythera Mechanism, dating to around 150 to 100 BCE, was an unparalleled feat of miniaturized mechanical engineering. Its intricate system of at least 30 interlocking bronze gears created a dynamic, clockwork universe where planetary motions unfolded automatically. This portable planetarium could predict lunar phases, eclipses, using the Saros cycle, and even track the 4-year cycle of Olympic Games with turn-of-the-crank simplicity. The mechanism's differential gearing, previously thought invented in the 16th century, physically modeled the moon's variable speed, a mathematical subtlety that wouldn't reappear in European instruments until the Renaissance. Its face displayed the cosmos as a living system, integrating Egyptian calendar data with Babylonian eclipse predictions and Greek geometrical theories. Astrolabes, developing later, perfected by 5th century CE Islamic scholars, took a more modular, user-driven approach. These flat planispheric devices consisted of stacked brass discs with rotating REIT networks representing fixed stars. Unlike the mechanism's self-contained calculations, astrolabes required manual adjustment for specific dates and locations. Their strength lay in versatile problem-solving, telling time by sun or stars, calculating prayer times, determining celestial altitudes, and solving spherical trigonometry problems through interchangeable plates for different latitudes. The astrolabe's stereographic projection, a mathematical technique possibly known to the mechanism's makers, compressed 3D celestial relationships into 2D, making it superior for observational astronomy, but less comprehensive in modeling planetary motions. Key differences emerge in their technological approaches. The mechanism's internal gearing automatically accounted for celestial cycles through mechanical analog computation, what we might call hardwired astronomy. An astrolabe, by contrast, functioned more like an analog computer where the user physically manipulated components to derive solutions. The mechanism showed changing celestial relationships over time. The astrolabe captured static snapshots requiring human interpretation. Remarkably, while hundreds of medieval astrolabes survive, the Antikythera mechanism remains unique, suggesting its extraordinary complexity limited ancient production, whereas astrolabe's relative simplicity enabled widespread use across Islamic, Byzantine, and European societies for over a millennium. Both devices shared common ancestry in Hellenistic astronomy, but reflected divergent evolutionary paths. The mechanism's disappearance with Greco-Roman civilization temporarily halted development of complex gearing, while the astrolabe's enduring utility made it the dominant astronomical instrument until the 17th century. Only when European clockmakers rediscovered mechanical computation would the Antikythera's legacy re-emerge in orreries and mechanical calendars, completing a 1,500-year technological circle. Together, they represent two faces of ancient ingenuity. One, a self-contained cosmic simulator, the other an adaptable mathematical toolkit for navigating both heavens and earthly affairs. In an era when science and philosophy were fused into a single crucible, and great inventions emerged from profound astronomical contemplations, the ancient world witnessed the appearance of complex mechanical devices, centuries ahead of their time. The Antikythera Mechanism stands as the sole surviving example of what was once a long series of astronomical instruments mentioned in ancient texts, but lost to time. Had fate preserved even a fraction of these mechanical marvels, our understanding of ancient technological progress might have been completely transformed. In his philosophical writings, Cicero described with awe the celestial sphere created by the great Archimedes, a device that meticulously replicated the movements of the sun, moon, and planets. This marvelous machine could predict solar and lunar eclipses years in advance, as if a piece of the heavens had been placed in human hands. Cicero's account was no mere admiring description, but living testimony to an advanced technology whose traces have largely disappeared. Most remarkably, Cicero recounted how the Roman general Marcellus kept one of these devices as a prize trophy after the fall of Syracuse, demonstrating its extraordinary value in that era. Yet Archimedes was not alone. Ancient texts speak of another philosopher, Posidonius, who created in Rhodes another celestial sphere that improved upon its predecessors. According to Strabo's writings, this sphere was an engineering marvel that displayed the complex motions of planets with astonishing detail. Reading these accounts, one might imagine descriptions of Renaissance instruments rather than devices from the 1st century BCE. Even poets fell under the spell of these astronomical devices. Ovid celebrated in his Fasti small celestial spheres that displayed the boundless universe. These poetic references were precious hints at the spread of this technology among the Roman elite. In later ages, the historian Procopius mentioned a mechanical universe in the Constantinople palace, suggesting these engineering traditions persisted until the 6th century CE. The greatest mystery remains: how did all these brilliant devices disappear, leaving only the Antikythera mechanism? Perhaps most were made of valuable bronze that was melted down during turbulent times. Or maybe this technology remained restricted to a small elite circle, with only a handful ever produced. Whatever the reason, these texts prove the Antikythera mechanism was no historical anomaly, but part of a complete scientific mechanical tradition. Reading these ancient accounts leaves profound sorrow for the tremendous technological heritage we've lost. Had even one of those celestial spheres described by Cicero survived, or one of Posidonius's celebrated devices, we might be looking at a completely different chapter in the history of technology. Yet even with this tremendous loss, the Antikythera mechanism remains a silent witness to an era when theoretical science and practical engineering were inseparable twins. Ultimately, these texts raise a troubling question. How many other brilliant inventions might have vanished without trace? And how many truths about our civilization's progress lie buried under the rubble of time? Perhaps the most important lesson from this story is that technological progress follows not a straight ascending line, but a winding path where great achievements may disappear for centuries before being rediscovered.